Hello, dear learners, and welcome back to the Lesson BCE YouTube channel. Today, we're jumping into a brand new explainer, Introduction to Astronomy. We are going to cover what astronomy actually is, how we observe the night sky, and how scientists measured those mind-boggling astronomical distances. We are literally starting from the stars right in our own backyard and going all the way to the deepest edges of the visible universe. Please don't forget to subscribe and like our channel to support us. All right, let's get right into it. So here is our roadmap for today. We'll be looking at what is astronomy, the celestial sphere, seasons in apparent motion, measuring the solar system, and finally, the cosmic distance ladder. Let's kick things off with Section 1. What is astronomy?
You know, long before modern astrophysicists were using high-tech satellites to measure dark matter, our ancient ancestors were looking up at the exact same sky. The stars were, quite literally, the lights our ancestors learned to tell time and find their way by. They looked at these seemingly random scatterings of stars and mentally grouped them into recognizable shapes, what we now call constellations. By naming them after gods, heroes, or animals, they basically built a brilliant, reliable map to navigate the night.
Now today, it's a bit harder to see that map, right? City lights and bad weather really get in the way. So to fix that, we have planetariums. A planetarium is an awesome indoor facility that simulates the entire sky for you, completely free from light pollution. On the flip side, we have observatories. An observatory is a dedicated scientific facility packed with powerful telescopes used to directly observe the actual, real objects out there in space. Moving right along to Section 2, the celestial sphere. Imagine yourself standing outside, looking up. The heavens basically look like a massive curved dome arching right over your head. Astronomers call this the celestial sphere. It's a really handy model because you can pinpoint any star's location on this giant invisible dome using a set of coordinates called altitude and azimuth. It's like a GPS grid for the night sky. But here's the tricky part. How do you translate a 3D dome onto a flat 2D map? It definitely causes some distortion. To solve this, astronomers use a stereographic projection map. What this does is preserve the shapes of small areas, meaning those recognizable constellation patterns stay accurate. So even if the very edges of the map look a little stretched out, you can still easily chart and find your favorite stars. The coolest part, though, is that you don't even need a fancy map to measure the sky. You can literally just use your hands. There's an activity called spanning the night skies, where you hold your hands out at arm's length against the sky. Just by doing that, you can estimate the altitude of a star or figure out the angular separation between two objects, like the stars that make up the summer triangle. It's a super fun, hands-on way to connect with the celestial sphere. That brings us to Section 3, Seasons and Apparent Motion. If you're patient and watch the sky over several months, you'll notice things change. As the Earth revolves around the Sun and the planets actually appear to move along a very specific path across a backdrop of distinct star patterns. And this specific group of background constellations, that is what we call the zodiacal constellations. Against this fixed backdrop of zodiac stars, the planets act like little wanderers. Because our solar system is mostly flat, the planets all appear to move along roughly the same line in our sky, generally traveling from west to east. But they don't all move at the same pace. Mars, which is pretty close to us, zips right along. But a planet further out, like Saturn, it creeps across the sky incredibly slowly. But wait, it gets weirder. Sometimes, these planets seem to completely break the rules. They will perform this tiny, temporary reverse motion, appearing to drift backward from east to west before resuming their normal path. Astronomers call this retrograde motion. Now, the planet isn't actually moving backward. It's just a totally wild optical illusion caused by the different orbital speeds of Earth and the other planets as we all race around the Sun. Okay, let's jump into Section 4, Measuring the Solar System. You might be wondering, how do astronomers actually know the mathematical distances to these planets? Miles and kilometers just do not cut it when you're talking about space. It's too big. So they start with a foundational baseline called an astronomical unit, or AU. An AU is simply the average distance between the Earth and the Sun. It's basically our local cosmic yardstick.
But once we look outside our solar system, even the AU is way too tiny. For that, scientists use a unit called the parsec. A parsec is absolutely massive. It's roughly equivalent to 3.26 light years. To put that into perspective, that is over 3 × 10 to the 13th power kilometers. Seriously, just a staggering distance.
So how do we actually calculate a parsec? Astronomers use a geometric trick called stellar parallax. Think of it like a giant triangle in space. A parsec is defined as the distance to a star that has a parallax angle of exactly 1 arcsecond, using a baseline of exactly 1 astronomical unit, which, remember, is the distance from the Earth to the Sun. Basically, by measuring how much a nearby star appears to shift against the background stars as Earth orbits the Sun, we can calculate its exact distance.
And finally, Section 5, the cosmic distance ladder. Measuring the entire universe is kind of like climbing a giant ladder. You need different techniques for different rungs. For the first rung, the stars relatively close to us in the Milky Way, we use that stellar parallax trick we just talked about. But for distant galaxies, parallax doesn't work. The angles are just way too small. So astronomers have to switch to completely different techniques to build the next rungs on this cosmic distance ladder, allowing us to reach further and further into deep space. To measure those truly vast distances, astronomers look for something called standard candles. These are specific celestial objects where we know their exact true luminosity, meaning we know exactly how much light they actually emit. By comparing this absolute, true brightness to how dim they appear to us here on Earth, we can do the math and find the distance. Key standard candles include pulsating stars known as Cepheid variables and even massive supernova explosions, which are so incredibly bright they act like cosmic lighthouses billions of light years away.
And that brings us to a mind-bending mystery. When scientists use these tools to calculate the mass of nearby galaxies, like Andromeda, based on the visible light of the stars, the math doesn't add up. The stars at the outer edges of Andromeda are orbiting way faster than their visible mass predicts. There has to be an additional gravitational force pulling them. So if there is extra mass out there that we literally cannot see, matter that doesn't emit or reflect any light, what invisible forces of dark matter are still out there waiting for us to fully understand them? It's a massive puzzle. Well, thank you so much for learning with Lesson BCE today. Don't forget to subscribe, like, and share the channel. See you in the next lesson.